In the last video, we summarized this diagram. And the idea was when we get the raw audio from our microphone, we represent it as an array of bytes where the indices represent times and the values represent the amplitudes of your audio wave at those times. Then what we do is we take 4,096 values, which represent about 1/10 of a second of audio, and that's the input to the fast Fourier transform method. That method gives an output that's an array of complex numbers. It's not so important what a complex number is or why it happens right now, but what you need to understand is that the indexes represent different frequencies, and the values, the complex numbers themselves, if you take their absolute value, it's going to give you a double that tells you the loudness of that frequency. So for example, index 1 corresponds to 10 hertz, which is a very, very low sound. And the absolute value of its number will tell you how loud that particular sound was in the 1/10 of a second of audio we gave it as an input. So each of these values sort of spreads out in the original sound. How loud are all of the different pitches that make up that 1/10 of a second of sound? You also saw that the spectrograph is a graph which shows you that fast Fourier transform output. You've got time on the x-axis, and each individual column, each 1 pixel column represents 1/10 of a second of audio. And then on the y-axis, you have pixels that range from very low frequencies at the bottom of the graph to very high frequencies at the top of the graph. And the brightness of the pixel tells you how loud the different frequencies are. So it's a lot clearer if I whistle. So you can see that the loud frequencies went from low to high as I was whistling. Those frequencies, the loudnesses of those different frequencies are what we're going to use to get a fingerprint of audio every 1/10 of a second. And that fingerprint is what we're going to use to look up in our hash map to identify whether or not we've heard this audio before, whether or not the audio is part of our pre-recorded library. So the way we're going to do that is we're going to identify certain intervals of frequencies. So we're going to look at frequencies between 440 hertz and 1200 hertz, between 1200 and 1800, between 1800 and 3000. If this is the spectrograph, then you saw that we've got, let's do this in a different color. You saw that it's going to display a vertical column where some of those pixels are brighter than others. What we're going to do is we're going to loop over all of the values in each of these intervals, and we're going to find the one value that's the loudest. So if I was going to put a red dot at the loudest interval, it would look like this. And so that's going to give us several numbers, and those numbers are going to be our fingerprints. So here I'm actually plotting them in the spectrograph, and so you can see a scatter of red dots. And it looks like the dots are everywhere, but for each column there's exactly 3 dots. It just looks like a scatter because they're moving around with every single pixel I move over. It's going to be a lot clearer if I whistle. You see that the red dots that are identifying the loudest frequencies are tracking the frequencies that I'm whistling at. So how is this going to work in code? Go ahead and go to your spectrograph plotter. The top section of this is hopefully familiar from things that we've done in class, but the general idea is we've got our audio reader object, and we've got our byte array output stream object. Inside setup, we have our audio reader initialized to a mic stream. And then we tell our audio reader to give us the output stream for the microphone. Inside draw, we tell the output stream to return the raw recorded audio values since the last time we asked, and then we have it reset its memory buffer. This is the line that actually performs the Fourier transform. And if you need a reminder, go back to the last video. But the inputs that we're giving it are the raw audio. We're telling it the window size. So that was 4,096 numbers from our array, and that corresponds to about 1/10 of a second of audio. And then we're giving it this variable. And if you go to the top, this variable is an array list of complex number arrays. Here's a way of thinking about what that's doing. When I run perform FFT on the raw audio output array B with a window size of 4096 and the FFT frames array list, here's how you can visualize the data. So B is the raw list of numbers. Those are the amplitudes at different time intervals. Every 4096 values represents about 1/10 of a second. So what this method does is it takes an array that might be very long and it divides it into lengths that are 4096. And then it runs the fast Fourier transform on each 1/10 of a second of audio. So it's going to take the audio represented by these 4096 and it's going to do the fast Fourier transform. And then the results are going to get added to the end of this array list. So at the beginning, our array list is empty, so it's going to perform the Fourier transform on these numbers, and the output array from the Fourier transform is going to get put in element 0. Then it's going to perform the Fourier transform on the next 1/10 of a second of audio, and this output array is going to get added here. So each element in the array list represents the output for 1/10 of a second of sound, and what's inside is an array of complex numbers where the index represents the frequency of the sound and the value, if you take the absolute value of the complex number there, it will tell you how loud that frequency is in that 1/10 of a second of sound. So again, reference the first video if that piece is still confusing. So what we want to do is for each of these arrays, we want to loop between particular frequencies, and we want to find what's the loudest frequency inside particular ranges. So back in the code, now I told you how this method is loading this array list full of the arrays that we want. Here we're saying as long as we haven't processed all of the audio that we've generated the outputs for, let's go ahead and remove the oldest answer, like the frame that we've added the longest time ago. So it's the 1/10 of a second of audio that we haven't processed yet. And that's what this frame is. So I've written a helper method in the spectrograph plot, which will take those frequency volumes and display them in a single vertical column, because that's what the spectrograph does. What you're going to do is add these lines of code. So inside our fingerprint lib, we're going to write a method where we give it all of those loudnesses of different frequencies that come as the output of the Fourier transform. And it's going to tell us just which ones are the loudest frequencies between certain frequency intervals. That's the output. And then to see what they are, we're going to print them. So right now, this is unimplemented, so it should just print zeros. But let's go ahead and go inside there and talk through a bit of pseudocode. If you're on a PC, you can hold the Control key and click on the method. If you're on a Mac, you can hold the Option key and click on the method, and that will jump you straight to where the method is declared. Otherwise, you'd want to actually navigate there manually by going to Model, finding Fingerprint lib, and scrolling down to approximately line 130. Nope, my mistake. In your version of the code, it is line 124. So here's what it looks like. Get key frequencies 4 inside of fingerprint lib. So let's write the first little bit together and think about some of the pseudocode. So first we want to define the frequency ranges that we want to get out the loudest frequencies for. So I'm going to call it ranges. And I'm going to type these numbers and then I'll kind of tell you what they're about in a minute. So let's do 44, 120, 180, and 300. Remember what this represents. The complex array results, the indices are telling you different frequencies, and the values are complex numbers whose absolute value will tell you the loudness of that frequency. And so this single array corresponds to a vertical column in the spectrograph. So our results array, all of the loudnesses are telling us the pixel value, the pixel brightnesses at all those different frequencies. So what we wanted to do is we wanted to loop between 440 hertz and 1200 hertz and find the loudest frequency, and loop from 1200 to 1800 and find the loudest frequency, and so on. So how's that going to look in pseudocode? Remember that each index multiplied by 10 gives us the frequency that that index represents. So if I want to loop from 440 hertz to 1200 hertz, what that really means is I'm going to be looping from index 44 up to index 120. So I'm going to be looping between two indices inside my array, and I'm going to look at all of the loudness values and figure out at what index do I see the loudest value inside that interval. And that's the index that tells me the frequency where my loudest note is going to be. So what's that going to look like in pseudocode? Let's write it. So I want to loop over ranges somehow. Except I want to loop over every pair of indexes and ranges, because these are giving me my starting and my ending point for the intervals I want to loop over. So let's make some variables. So like low index is going to be ranges I, and then high index is going to be ranges I plus 1. Once I have those two, and remember the indexes correspond to a low frequency and a high frequency, what do I want to figure out? I want to figure out loudest frequency in that range. So let's make a helper method. Let's call it get loudest value in, or let's say between, and then you can give it the low index and the high index for your results array. So then you would write the helper method where you'd loop between the low index and the high index and find the loudest value. But then you want to return the index where the loudest value happens, and that's the loudest frequency. We probably shouldn't call it get loudest value. We should probably call it get loudest frequency or index. And then once you have that, we should probably save it in an output array. So let's make an output array. And I think I want my output array to match the number of intervals that are defined by my ranges. So here I have 1, 2, 3, 4 endpoints, but the endpoints are defining 1, 2, 3 intervals. So you can see that the number of intervals is always going to be one less than the number of values in ranges. So let's make a new int array whose length is going to be ranges.length minus 1. So now all I need to do is save my loudest frequency inside my output array, and then at the end you can return your output array. And that's it. Okay, everybody, you're doing great. I know this is a tough application, but the amount of effort you put in is gonna make you feel so proud when you're done. Good luck.